Swayam Prabha. Digital India. Educated India.
Alright, so now let's get back to the electrophilic aromatic substitution with other electrophiles. So far we have been looking at, for example, bromination. So the basic reaction, just to recall, is basically a reaction of an electrophile with benzene to give you the electrophilic aromatic substituted product, which is this, right? Now the electrophile can actually be a variety of compounds. And so, for example, the electrophile that we can think about is one of the most important reactions that organic chemists are interested in, which is the formation of a carbon-carbon bond. So how do we generate carbon-based electrophile, right? So this is something that we have looked at previously. So for example, carbon-based electrophiles can be produced as intermediates during SN1 reactions. So for example, here if you have an alcohol such as this, and if you expose this to H+, right, and based on the SN1 mechanism that we have previously looked at, right, or E1 for that matter, we are familiar with the formation of protonation of this center. So it's going to form OH2+, and if you were to draw the arrow pushing mechanism, so it looks like this. This is a lone pair on oxygen. It attacks here and gives you the OH2+. And now you can propose this carbon-oxygen bond being broken because water is an excellent leaving group. So you would end up producing tertiary carbocation over here as well as water, right? So this is something that we already know, okay, from our previous courses. So therefore, the formation of the carbocation is something that we have some prior exposure to. So now the question is, can we put both of these in the same bottle? And that is what we want to do if we want to do, Friedel-Crafts alkylation reaction. So the reaction is as follows. So you need to be able to generate a carbocation in the presence of benzene, and one of the ways in which you could do this is to react it with an alkyl chloride in the presence of a Lewis acid, okay, such as AlCl3, right? So we've already seen prior that when you have Br2 in the presence of AlCl3, you have a weak bond that is being formed with aluminium, and this aluminium is then gives rise to a complex such as this, where you have this being kicked off and giving you Br+, which is the active electrophile, and AlCl3 Br minus, and so this is the role of aluminum chloride. So if you were to think about a similar role for this group over here, then you can imagine that instead of the bromine, you can have the chloride can be lost by using sort of this chemistry. Okay, so now let's look at this. So instead of bromine, we now have tertiary butyl chloride, right, this compound, and you have lone pair on Cl, and that's again going to coordinate with aluminum chloride, and this is going to result in the formation of a complex such as this Cl, where it's going to be bound to AlCl3, and then you can push electrons in the following manner and gives you the formation of this bond, and it's going to give you the tertiary butyl carbocation as one of the products. And now you know the rest of the chemistry. It's fairly straightforward. So when benzene reacts with a carbocation, you're going to have the formation of the intermediate that we discussed earlier, which is going to give you this kind of a intermediate, right? And the hydrogen over here, and you have a positive charge being formed, and the rest of the bonds are essentially the same, right? So now this is the intermediate that we're looking at, and as we discussed earlier, there could be some base, maybe there is some amount of chloride that is floating around as a dissociation of this complex, and it attacks, and you have a loss of a proton essentially to give you the product, which is nothing but the alkyl benzene, right? So which we should look at in the next slide. Right, so you have this kind of a compound, and if you lose a proton, maybe there's some mild base such as chloride ion being present, and it's going to give you the desired product, which is this. Okay, so this is something that we could straightforward maybe could propose, and this is essentially called as the Friedel-Crafts alkylation reaction. Okay, so again, as I said, the name is not very important here, but you need to understand the mechanism. All right, now let's go back to the example of SN1 reaction. So here, if you imagine that the carbocation is indeed being produced when you take a tertiary butyl alcohol and add H+. So under these conditions as well, you would get Friedel-Crafts type of reaction. And if you add benzene here to this, then the product that you're going to get is this. I would urge you to go back and solve this problem, work out the mechanism of this reaction. Okay, so this is an assignment for all of you. Go back and do this. So let's start this part of the lecture with a problem. So the problem that we're looking at is a nice mechanistic question. So we all know that when you react benzene with bromine, there's basically no reaction if you do it in the dark, and you need a loose acid such as AlCl3. Okay, but this reaction to give you the product bromobenzene is possible if you add a small amount of catalytic pyridine. Okay, so just to give you the structure of pyridine is this, the nitrogen. So if you add a small amount of pyridine, the reaction goes forward and gives you the product bromobenzene. Okay, so the question is, what is the mechanism of this reaction? All right, so all of you work on this, and we will take this up sometime in the next few lectures. All right, so now I want to discuss now in this lecture the sort of energy profile associated with the electrophilic aromatic substitution. So just to be clear, we normally represent the energy profile in the following manner. We have a x-axis and a y-axis, and so the x-axis is basically reaction coordinate. Okay, so some people also call it progress of reaction, and this is energy, right? So when we want to start, we would start with the starting compound, basically benzene, and I'm just going to draw benzene and a generic electrophile. Okay, so let's call it E+, and so let's say this is the energy level that we are starting. Okay, so here is the energy of the starting material, right? Now we know that the first step of the reaction is actually to form the intermediate. The intermediate is basically the complex where the aromaticity has broken, and that structure is as follows. So you have E and then you have H, and then there is a positive charge over here. And so this is going to be the structure of the complex. And now, based on what we sort of know about this, it's quite likely that the energy of this complex is substantially higher than that of the individual starting compounds, because the intermediate actually has lost aromaticity in its structure, right? So therefore, if you want to look at it, you can consider that the product or the intermediate that is formed is going to be quite highly energetic. Okay, so what I'm doing is I'm just trying to get this intermediate out of the way so that we can draw the remaining structure clearly. All right. Nevertheless, so now the product that is going to be formed is basically the electrophilic aromatic substituted product, which is basically E, and you're going to get a byproduct of H plus, right? So which is going to be basically the loss of proton, right? Now, if you want to look at this, many of the electrophilic aromatic substitution reactions are actually exothermic in nature, and so you would imagine that the product is going to be more stable than the starting material. So this is going to be my delta H or delta G. Okay, and now coming to the sort of intermediate over here, we're going to try again to see if this intermediate can be moved. And yes, this time I'm able to select all of the structures, and I'm just going to move it over here so that it's easy for us to draw out the energy profile. So I'm just going to call this as I, which is basically the intermediate. And so the I structure is over here. And now if I have to draw the energy profile, it's going to look something like this, right? So there's going to be a fairly high barrier to get to the intermediate. And then the intermediate is going to collapse and give you the product. All right. So now what we know based on Hammond postulate is that the transition state, which is approximately here, the transition state is going to resemble the product, which means that, essentially the Hammond postulate says that in a highly endothermic reaction, the transition state, sort of resembles the product. And as a corollary, in a highly exothermic reaction, the transition state resembles the starting material. Okay. So therefore, in electrophilic aromatic substitution, you can imagine that the intermediate that is formed is going to be of high energy, and therefore the transition state leading to that intermediate is going to resemble the product. So a lot of this is going to be important when we want to understand the course of a reaction, for example, from a regioselectivity standpoint, right? So from your prior courses that there is a distinct orthopara selectivity versus meta-selectivity and so on. So all of this can be explained using this concept. All right. So just to complete this diagram, this sort of measure here is going to be your activation energy, or delta G double dagger. Okay. So that pretty much takes care of the electrophilic aromatic substitution. And now you will notice that the barrier for the second reaction, or the reaction of the intermediate, is not very, very high, because you would assume that the intermediate is going to collapse fairly rapidly and give you the product. There are examples in the literature of extremely stable intermediates, that is, they hang around for a fairly large amount of time, but most of these intermediates are actually quite unstable. Okay, so that sort of brings us to the conclusion of this energy profile. And to summarize, the reactions of electrophilic aromatic substitutions are usually exothermic, and not necessarily so, but many of them are exothermic. And the formation of the intermediate, which is the first step, is the rate determining step. And the transition state leading to the formation of the intermediate actually resembles the intermediate, and therefore a lot of the stability issues can be taken care of by understanding this concept. All right, so now let's move on to the next topic, which is basically Friedel-Crafts acylation reactions. And so Friedel-Crafts acylation reaction basically depends on a very important sort of reaction that some of you are already quite familiar with, which is basically when an acid chloride reacts with a Lewis acid, such as AlCl3, right? So you can apply the same principles that we looked at previously, which is that the aluminum is going to start coordinating with the fluorine, and it starts pulling electrons in this direction, right? And so once that happens, you're going to generate R C double bond O Cl, and then there's going to be a complex with Al Cl3, and this is going to eventually produce, the electrons are going to be pulled from here, and while those electrons are being pulled, it's also likely that the lone pair of oxygen is in play and it moves over here. Okay, so if you write out the product that is formed, you will get R C triple bond O with a positive charge, and you would get Al Cl 4 minus. Okay, so this is the kind of intermediate that you start producing, and so therefore RCOCl in the presence of aluminum chloride is going to generate highly reactive electrophilic species, which is RC triple bond O plus. Okay, normally if you have water or something, then this is going to get hydrolyzed and give you a carboxylic acid. But since we are dealing with electrophilic aromatic substitution reactions, this intermediate that is produced is going to react with benzene, and RC triple bond O plus, this is going to react with benzene, and you're going to end up with an intermediate such as this, right? C double bond O R, and then this hydrogen is going to remain the way it is, and the other double bonds that are shown here will continue, and there's going to be a positive charge. Okay, so now when you do this, you end up with a situation where you're going to have possibly a loss of proton, which is going to occur in the presence of a base. It attacks and regenerates the aromaticity, and it gives you the product, which is the acylated benzene. Okay, so if R is basically CH3, then you will start with acetyl chloride and you will get acetophenone, and so on and so forth. So this reaction is called the Friedel-Crafts. So the Friedel and Crafts were actually two different people who got together and discovered this acylation reaction first, and then subsequently they also found the alkylation reaction. Okay, so this is known as Friedel-Crafts acylation reaction, and as we looked at previously, it's not important for us to know the name of the reaction, but it's important for us to understand the mechanism and also the implication of this reaction. So just to understand the energetics of this process, so we have a very similar energy profile to what we looked at in the previous case. So you have R C double bond O Cl. It's going to that is the energy that we're looking at, and now the product that is going to be formed is R C triple bond O plus Cl minus, and if you're doing it in the presence of aluminum chloride, it's going to give you, that's going to catalyze the reaction. So this is going to give you intermediate here, which is this. Okay, so this is going to be the first step of the reaction. I'm just going to redraw this so that it's a little clearer over here. So basically this is R C 1 2 3 oxygen, and then there is a positive charge. Okay, so this positive charge is going to be mainly located on the oxygen, right? So we'll get back to that concept a little bit later during the problem solving session, right? And the rest of the energy profile would be identical to the reaction of benzene with an electrophile. So this is going to be the important step in Friedel-Crafts isolation, is the generation of the electrophile. The next important steps are described in the previous section, which is basically the electrophilic aromatic substitution, the general mechanism for that. Okay. Now, if you can do this, if you understand this reaction, now let's look at a problem that will help us put a little bit of perspective into this reaction. So the problem is as follows. So you start with this very interesting compound, which is 1, 2, 3, 4 Cl. Okay, and if you want to number the carbons, it's going to be 1, 2, 3, 4. It's 4 carbons, and then expose this to aluminum chloride. I get a product which essentially has M by Z, which is M by Z is basically mass spec. When we record the mass spectrometry, then we get a mass by charge ratio, and the M by Z is we get a peak at 146.07. Okay, so the question here is, what is the product that is formed? Okay, so you can take some time and work on this problem. We'll take this up again in a subsequent lecture.